Good evening. Not feeling well. It's a bit of sore throat, so I was not able to record yesterday any video. Anyway, today feeling better, so started with it. Let me share my screen. Okay. So if you remember, we had been working on work energy power, and in the previous video, I think on the Thursday's video, we looked out like how to find out the stopping distance or work done by the frictional force. And we use two methods here. That's what we had done. Okay, kinematics and as well as work energy power. Now let us look at one more problem. Okay, on work energy power. Okay, in this problem, I'm not going to show by two methods, but there's a conceptual mistake. So I'm going to highlight that. Right, let us read this work energy theorem as applied to oscillations. So a block of mass 100 grams is moved with a speed of 5 meters per second. Okay, at the highest point in a closed circular tube of radius 10 centimeter. So you have a closed circular tube like this, and let us say this is the container. This is a container like this. Assume it's a circle. It doesn't appear to be like a circle, but anyway, okay. So you keep a block here, and then this mass of this is 100 grams. Mass is 100 grams. The speed of it. Now what you do is you give a push here. You give a push. Whose speed is 5 meters per second. Now it's a vertical circle. Okay. So therefore, this velocity is 5 meters per second. So don't consider that this is a vertical circular motion. This is what most of them do. At the highest point of radius 10 centimeter. That is radius. The cross section of tube is such that the block fits exactly into it. Okay, it exactly fits into it. The block makes several oscillations inside the tube and finally stops at the lowest point. So you give a push over here, 5 meters per second. Then the block starts moving like this. It goes inside the tube, moves the higher velocity. It goes until here, let us say, and once again it comes like this. Then it comes like this. It oscillates like this for some time, and later on, finally, it comes and lands here. Okay. Now, most of them, when they read this problem, they assume either this should be a circular motion or maybe an oscillatory motion. Let us see what this do. Find the work done by the tube on the block during the process. What is the work done by the tube on the process? Why should the tube do some work? Because it has to stop it, right? Definitely has to stop it. So why? How does it stop it? How does it work? The tube does some work. Maybe there's some friction, right? That's what we understand. So the question here can be asked as what is the work done by the friction also? Okay, either like this or it can be done due to the friction. So because of friction, what happens is the speed at which you throw here, it is unable to come upwards here. Otherwise, definitely this is your potential energy and kinetic energy here. Now, as it goes down, all the potential energy will get reduced to kinetic energy, get converted into kinetic energy. And when it comes here, so the kinetic energy will be much higher, and thus it keeps on moving like this. That's what should happen. Okay, so you should see that the difference in work should have been. So usually what they do is they consider like this. Okay, so mv square by r. Okay, what is the formula here? Now you see, since it's a circular motion, student responds like this. The centripetal force over here should be equal to weight. Okay, as a result of it, it keeps moving on like this. And then what they do is they write mv square equal to mgr. Of course, this is also not correct. Okay, and then we know that mv square equal to mgr from here, pushing this other side. And work done in lowering the speed is nothing but half mv square. So what they do is they consider this as half mv square, and finally they write like this. And some of them, what they have done is, this is the most of the time they do this. So as a result of it, they substitute the value of mgr. What is m? 100 grams is 0.1 multiplied by 10 multiplied by radius. What is radius at 10 centimeter? So 10 centimeter is 0.1 divided by 2 will be equal to how much? 0.05 joules. This is the answer most of them have written. Let us see how to solve this. See, first of all, this is neither a problem on circular motion nor on oscillations. So what is that been asked? Find the work done by the tube on the block during the process. You can just use conservation of energy, nothing else. Okay. So towards it. Now what is the work done? Now, how do we calculate work done? Find out what is the initial energy, then find out what is the final energy, and take the. Sorry, I got disconnected in between. Okay. Let me continue. So I was saying that You should use your conservation of energy theorem. So towards it now, you see it starts from here. It keeps on going like this. Okay, and some students what they do is they use the COE correctly, conservation of energy theorem correctly. But what they do is they find out that if this is half mv square, they will write like half mv square plus mgr should now be equal to half mv2 square plus 0. They write like this. Okay, and finally they think that this v2 square is something else. It will be a higher velocity. Why? Because they assume it here. But read the question once again here. It says, okay, the block makes several oscillations. Of course, V2 is nothing but the velocity at this point. Okay, I don't deny that. But definitely this value of V2 will be much larger because it become mgr plus, sorry, mg into 2r, 2 mgr into so much. Okay, that's true. But what happens is the object takes up this velocity, climbs upwards, and then once again it comes like this. Now it keeps on oscillating like this, and finally it comes to 0. So your final velocity V2 should be equal to 0 here, right? That's just what we should do. So in other words, the work done should now be equal to the initial energy minus final energy. Okay, if I take the magnitude. Now what I do is initial energy is should be equal to half mv square plus 2 mgr. Why 2 mgr? Because you see, I'm taking this as my reference. Okay, minus. When it comes to rest, it is 0. And when it comes to rest over here, potential energy is also 0, minus 0. What did I do? I took the difference between this energy. Definitely difference between this energy would be equal to the work done by the friction. Now let us do this. Now this should now be equal to m into v square by 2 plus what do I get here? 2gr. 2gr. Now let us calculate this. What is m? 0.1. 0.1. V square. What is v square? 5 meters square, which is 25 by 2. 25 by 2 plus 2gr. 2 into 10 into what is radius? Radius 10 centimeters, 0.1. 0.1. Okay. So therefore this goes away. So 12.5 plus 2 is equal to 14.5. 14.5 into 0.1 should now be equal to 1.45. Okay. So this should be your work done. 1.45 joules. So the work done here is equal to 1.45 joules. Quite easier, right? Okay. We should understand the problem here clearly to get a correct answer. Okay, guys. Thank you for watching. If you like this video, do subscribe to my channel and share this with your friends. Let me do 1 or 2 more problems in work energy. And my next topic, as many of you have written me mails, is or will be COM. What is COM? Center of mass. Okay. So we'll be working on center of mass because they said, okay, center of mass is quite confusing. Using formula level, you can easily do it. But if it comes out to be something like situation based, 2 objects are kept on top of the other, how do we find it out? What is the center of mass of a circular hole and so on? Okay, something like I have an object, a small hole has been cut into it. How does the center of mass change? Okay, so these kinds of questions, so they are not able to answer it. So as a result of it, they had been asking me, so how do I solve such kinds of problems? So I'm planning to do problems based on it. So let us see. Maybe I can have one more lecture on this, on work energy power. And still, if you have some doubts on WEP, you can definitely mail me up those problems. I'll be happy to work out on this. Thank you, friends, for watching this video. Thank you once again.